Hey guys, and welcome back for another lesson on probability. Today we're looking at combined probability and using tree diagrams to graphically represent all of the possible combinations of outcomes. My name is Miss Danielson, and let's just get into this. Let's start out with some of the basics, but be warned, this is not an introductory lesson. If you need an introductory lesson on probability, check out the description box below and come back when you're ready. First of all, you should know that the probability of any specific outcome for any event is always given in fraction or decimal form between the values 0, which would be an impossible event, and 1 being a certain event. You can't have a probability greater than 1, nor could you have a negative probability, obviously. So for example, the probability of rolling a 3 on a fair 6-sided die would be 1 out of 6, because there is one side of the die that's got a 3 on it, and there are 6 possible outcomes altogether. Also for this lesson, you're going to need to remember what it means to define two events as being independent. Two events are independent if the outcome of one has no impact on the likelihood of the other's outcome. For example, if I roll a die, the outcome of that die will not affect the outcome of me then flipping a coin. Those two events would be considered completely independent. If events are independent, we can use the AND rule. That is, the probability that one event happens and another event happens is calculated by simply multiplying those two probabilities together. For example, the probability that I roll a 3 on a fair 6-sided die and then I flip a heads on a coin would be simply the probability of rolling a 3 multiplied by the probability of flipping a heads. The probability of rolling a 3 is 1 over 6. The probability of flipping a heads is 1 over 2. That's a combination of outcomes, and their probability of happening together is 1 over 12. This rule should not be new for you, but take care not to confuse the AND rule for independent events with the OR rule for mutually exclusive events. Two outcomes are mutually exclusive if one outcome occurring makes it impossible for the other outcome to also occur. For example, if I roll a 3 on a fair die, it could not possibly also be a 4. Those two outcomes are mutually exclusive because obviously if I roll a die, the outcome is either a 3 or some other number, but it can't be more than one number at the same time. However, the outcomes of rolling a 3 or the outcome of rolling an odd number are not mutually exclusive because the outcome could be a 3 and an odd number at the same time. So rolling a 3 and rolling an odd number are not mutually exclusive events. Because if I were to say, what's the probability that I roll an odd number or a 3? Well, I've already included the probability of rolling a 3 in the probability of rolling an odd number. So keep this in mind when we start talking about the OR rule. The OR rule can only be applied to mutually exclusive events. The probability that one or another mutually exclusive outcome occurs is calculated by adding their probabilities together. So for example, the probability that I roll a 3 or a 5 on a fair 6-sided die can be calculated by adding their probabilities because rolling a 3 or rolling a 5 are two mutually exclusive events. It can't be a 3 at the same time as it is a 5. So the probability of rolling a 3 plus the probability of rolling a 5. Remember, we've got a common denominator. That does not change. We're just adding our numerators. 1 plus 1 is 2, so 2/6, or simplifying to 1/3, dividing both top and bottom by 2. Now, I hope you're with me so far. Feel free to hit pause to take notes and think that over before we go any further, because you need to have the OR rule and the AND rule, as well as independent and mutually exclusive, very clear in your mind before we go any further. Next, let's have a look at what happens when we add together the probabilities of all possible mutually exclusive outcomes. That is, the probability that any of the possible outcomes happen. Either this happens or it doesn't happen. Now, if I'm adding together all possibilities, the total probability should be 1, because remember, that's the highest possible probability. That means certainty. Now, the easiest way to explain this is to think of the probability that something happens or it does not happen. For example, the probability that it either rains or doesn't rain includes all possible outcomes. I am certain to get it right if I bet that it either rains or doesn't rain tomorrow. The probability that it rains plus the probability that it doesn't rain must add up to a total of 1 because these are all possible outcomes. So it really doesn't even matter what the probability is that it rains because the probability that it doesn't rain would be the rest of the probability. So from here we can deduce that the probability that any event does not occur can be calculated as 1 minus the probability that it does occur, because this should include all possible outcomes. Hopefully you're familiar with this notation. This big A here is some outcome, whereas this A with this little line up the top is not A. This is the event that anything but A happens. So I've used the same notation down here, R being the outcome that it rains, and R with this little line being the outcome that it does not rain. Now, hopefully you understand all of the basics that we've just been through so that we can get into our lesson now. Let's have a look at combined outcomes now, where we repeat an event several times and have a look at the combinations of possible outcomes. Read the question very carefully to know which outcomes we're interested in. For example, if Tommy rolls an ordinary, fair, 6-sided die 3 times repeatedly, I might be tempted to write all of the possible outcomes, being a 1, 2, 3, 4, 5, or 6 on the first roll. Then the second roll might have been a 1, 2, 3, 4, 5, or 6. And the third roll could also be a 1, 2, 3, 4, 5, or 6. But so far this tree diagram is only showing the possibilities where I rolled a 1 on the first roll. And then from there I could have rolled a 1, 2, 3, 4, 5, 6, but I'm only continuing with my tree diagram from the outcome where I might have rolled a 1 again. What if I'd rolled a 2 on the first roll? Well, then I'd have to have these branches coming off from that. And already you can see that this is going to turn into quite a mess. So rather than showing all of the possible outcomes, read the question through in full before you get started. Work out the probability that he rolls an even number more often than he rolls an odd number. Now, in order to draw a tree diagram for this question, I don't need to consider all of the possible outcomes, being 1, 2, 3, 4, 5, 6. I just need to consider the possible outcomes being either even or odd. So here's Tommy's first roll. He might have first rolled an even number or an odd number. Now I'm using this notation showing that this is even and this is not even. On his second roll, again, he might have first rolled an even and then gotten another even, or he might have gotten an odd after that. Or if his first roll was odd, he might have then rolled an even or an odd. You can see the combinations are adding up here. On his third roll, he might have rolled an even or an odd. This combination of outcomes shows that he rolled an even, then an even, then an even. This combination of outcomes shows that he might have rolled an even, then an even, then an odd. And this combination shows an even, odd, and even, and so on. I can show all the possible outcomes like this. Seeing these possible combinations, let's read that question again. Work out the probability that he rolls an even number more often than he rolls an odd number. So if he were to roll an even, well, he's obviously rolled more evens than odds there. If he rolled an even, and then an odd, again, he's rolled 2 evens and 1 odd, so that's more evens than odd. If he rolled an even, then an odd, then an even, odd, even, he's rolled an even twice and an odd once, so that's more evens than odds as well. But if he rolled an even, then an odd, then an odd, well, that would have been 2 odds and 1 even, so we're not going to include that possible outcome. If he first rolled an odd, then he rolled an even, and then he rolled another even, well, there he's rolled 2 evens and 1 odd, so that's more evens than odds. If he first rolled an odd, and then an even, and then an odd, well, that's definitely more odds than evens. Continue working your way down these branches to find all the possible outcomes that suit your question. If he rolled an odd, then an No, that's more odds than evens. If you rolled an odd, and then an odd, no, that's definitely more odds than evens. So these are the four possible outcomes where he's rolled more evens than odds. That's where he's either rolled 2 or 3 evens. We're going to use the OR rule for mutually exclusive events, and we're going to add their probabilities together. Now, in order to add these probabilities together, we must know what those probabilities are. This is a particularly simple case because the probability of rolling an even number or an odd number on a fair die, all of these possible outcomes have a probability of a half. So I've put my probabilities on each of the branches of my probability tree. And the way that I work out the probability of each combination of outcomes, I use the AND rule. The probability that I rolled an even on the first roll, and an even on the second roll, and an even on the third roll will be the product of multiplying 0.5 times 0.5 times 0.5. Now, just in this case, the probability of me rolling an even, then an even, then an odd will also be 0.5 times 0.5 times 0.5. I simply multiply together the probabilities on each of the branches that lead me to that combined outcome. And in this one case, all of these combined outcomes have a probability of 0.5 times 0.5 times 0.5. So I can simply write that as 0.5 cubed in all four cases. Now 0.5 cubed, that's 0.125. So 0.125 plus 0.125 plus 0.125 plus 0.125, that gives me 0.5. Now, this might have been a much more complicated way of working it out because I knew that all of these possible outcomes had the same probability. And there are 1, 2, 3, 4, 5, 6, 7, 8 possible combinations of outcomes, and I'm going to include 1, 2, 3, 4 of them. 4 out of the 8 equally likely possible outcomes has a probability of 0.5. Hopefully there's no surprise there. But again, this is a fairly simple example where all the probabilities were the same. So let's go on to something a little bit more challenging. This time Andrea is spinning a spinner 3 times, and the result is always either an even number or an odd number. Now, this is a spinner, not a die, and we're not told what the possible numbers are on the spinner. However, we're given this tree diagram to complete, and we're told that the probability of spinning an even on the first spin was 0.4. And we know that the even numbers plus the odd numbers make all possible outcomes, so the probability of rolling an even plus the probability of rolling an odd must add up to 1. So to complete this tree diagram, these two branches must always add up to 1. And 1 minus 0.4 is 0.6. So for our first branch, we've got 0.6 for the probability that we roll an odd. For the second spin, now this is a spinner, it should still have the same number of even numbers and the same number of odd numbers. I'm going to assume that the probability of spinning another even will also be 0.4, and the probability of spinning an odd will still be 0.6. Same thing as if I'd spun an odd number first. The next event should not be affected by the first one happening. The probability that I spin an even now should still be 0.4, and the probability that I spin an odd now should still be 0.6. So I can repeat these probabilities all the way along. Now that I've got my probability completed, let's try and work out the probability that she spins 2 even numbers and then an odd number. Read the question very carefully first. The order of the outcomes may or may not be important. It sounds here like the order is important. We first spin an even, then we spin another even, then we spin an odd. Let's find that on our probability tree. Even, even, odd. Following those branches, that's a probability of 0.4 and another probability of 0.4 and another probability of 0.6. Remember that these are independent events. The chance that I've spun an even on the first spin does not affect my chance of spinning an even or an odd on the second or third. So Our AND rule is that we'll multiply these probabilities together. The probability to spin an even, then an odd is 0.4 times 0.4 times 0.6, which is 0.096. Next, let's work out the probability that she spins more even numbers than odd numbers. That's the probability that she either spins 3 or 2 even numbers. Those are the combined outcomes of even, 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 odd, even, odd, even, or odd, even, even. And to work out those combined probabilities, again, we're using the AND rule for these independent events by multiplying the probabilities on each of the branches. So for even, we've multiplied 0.4 times 0.4 times 0.4. For even, odd, we've done 0.4 times 0.4 times 0.6. For even, odd, even, we've done 0.4 times 0.6 times 0.4. And for odd, even, we've done 0.6 times 0.4 times 0.4. Working that out, we've got 0.4 cubed, since we've multiplied the same value together 3 times. And notice these different outcomes are the product of the same probabilities. 0.4 times 0.4 times 0.6 is the same thing as 0.4 times 0.6 times 0.4. So I've got 3 of the same probabilities, so this might be easier for your calculation. Now that works out to be 0.33408. But generally on an exam, 3 significant figures is what's expected. So we've got 0.334 with a 0 after it. That's going to stay a 4. So I could just write that as 0.334. Now finally, at least. This is the last point I really want to drive home in this lesson. If ever you see the words at least in a probability question, consider the alternative. As we all know, the probability would add with all of the possible other outcomes to make a total of 1. So if you're asked, for example, to find the probability that she spins an even number at least once, consider the probability that she doesn't spin any even numbers. Because we know that the probability that she spins an even number at least once will be 1 minus the probability that she doesn't spin any even numbers. So looking at our probability tree again, the probability that she spins an even number at least once could be that she spun an even number 3 times, 2 times, 2 times in this order, once in this order, 2 times in this order, once in this order, or once in that order. Now that's a lot of probabilities to work out and add together. The only possible outcome that we want to exclude from this probability is this one, where she's spent an odd, and an odd. It's a lot easier to work out this probability and simply subtract it from 1 to find out this combination of possible outcomes. So the probability that she spins an even number at least 1 time is 1 minus the probability that she spins all odds. And that's 1 minus the probability that she spins an odd, which is 0.6, and an odd, which is 0.6, and another odd, which is 0.6. So that's 1 minus 0.6 cubed. 1 minus 0.216, which is 0.784. Now that's quite a high probability considering the total probability is 1, but look at all the possible ways that she could spin at least 1 even number. Once again, we've covered quite a lot of material this lesson, so if you need to hit pause now to go over your notes or take any notes, please do so before we go on to the practice exercise. Now with this practice exercise, take your time to read and copy the questions carefully and set up your tree diagrams to help you answer these questions. Make sure you've labeled each of the branches of your tree diagram with the probability of that outcome and list the possible combinations of outcomes at the end. You may want to work out the probabilities of these possible combinations on your tree diagrams to help you when you're answering your questions. Now there's another page of questions, so make sure you work through these ones first, and then we'll go on to the next set of questions. Once again, feel free to hit pause so you can go through that at your own pace. And when you're ready, hit play so that we can take up the answers. I hope you've had a chance to hit pause because here come the answers. For question 1, to complete this tree diagram, make sure that your branches add up to a total of 1. And your probabilities of your combined outcomes is a product of the probabilities on the branches. 2/5 times 2/5 is 4/25. Now that you've got a complete probability tree, you should be able to work out the probability that she wins both games. That's win-win. The probability that she loses both games, that's lose-lose. And the probability that she wins at least one game. So you could either do 1 minus the probability that she loses both games, or you could have added together all of these possibilities. I think 1 minus the probability that she loses both games would be the easiest way to work it out. Next, for question 2, finishing off that probability tree, again, the branches should add to a total of 1. 3/5 plus 2/5 make 5/5. 7/10 plus 3/10 makes 10/10. And completing the combinations of possible outcomes, either they both attend, he attends but she doesn't, she attends but he doesn't, or neither of them attend. The probability that neither attends the party is this one down here, 2/5 times 3/10. The probability that both of them attend the party is this one up here, 3/5 times 7/10. The probability that only one of them attends the party is either this one or that one. These are two mutually exclusive events, so I add them together. 9/50 plus 14/50. This is why it's helpful to leave our probabilities in the original format before we simplify them, because I got a common denominator here. 9 plus 14 is 23/50. For question 3, we weren't given any of the probabilities here. You need to work them out from the question. If there are 3 purples, 2 greens, and 5 yellows, 3 plus 2 plus 5, that's 10 counters altogether. 3 of the 10 are purple, 2 of the 10 are green, and 5 of the 10 are yellow. So I can write my probabilities of 3/10 or 0.3, 2/10 or 0.2, and 5/10 or 0.5. Now I'm perfectly happy to leave this as a fraction or as a decimal because my decimal values are exact. Had this been a recurring number or a number that I needed to round, I would rather keep it as a fraction. Now, since they tell us that we take a counter and then replace it, the probabilities of choosing a purple will be the same whether it's the first time or the second time, because we're constantly putting that purple counter back in the bag. So on the first time, there were 3 purple counters out of 10. On the second time, since I put that purple counter back, there are still 3 purple counters out of 10. So the probabilities haven't changed for the purple, green, and yellow. And the possible probabilities of the combined outcomes, I again work them out by multiplying the probabilities on the branches. 0.3 times 0.3 is 0.09. So what's the probability that the 2 counters have the same color? Well, that's either a purple, a green, or a yellow. For question 2, the probability that the counters are of different colors, well, that's 1 minus the probability that they're the same color, which I've already worked out. 1 minus all the probabilities I'm excluding. My probability is 0.62. Finally, the probability that I get at least one yellow counter, I can add together all the possible outcomes, which include at least one yellow. Or I could do 1 minus the probability that I get no yellows. Now there's lots of ways that I could get no yellows. I could get 2 purples, a purple and a green and a purple, a green and a green, but either way you get the same answer. This is simply going to be 1 minus 0.25, which is also 0.75. So you choose the way you find easiest for you to work out. For question 4, if the counters are not replaced, the probability is changing after we've taken a counter out. So the first time through, there are 3 purple counters out of 10 counters altogether. 2 green counters out of 10 and 5 yellow counters out of 10. But if I take out a purple counter, there won't be 3 purple counters anymore. There's 2 purple counters out of not 10 counters, but 9 counters now. There will still be 2 greens, but out of 9, and there will still be 5 yellows, but out of 9. And again, look at the set of branches. They still add up to be 9 out of 9. If I took out a green, there would still be 3 purples, but out of 9, but only 1 green out of 9, and 5 yellows out of 9. Again, add that set of probabilities together on those branches, and that makes 9 out of 9. And the same thing for the yellows. If I took out one of these 5 yellows, there would be 4 yellows left out of 9. The number of purples and the number of greens hasn't changed, but the total has changed. For the combined probabilities, again, we multiply together those branches, but I haven't turned these into decimal values because although this would be 0.3, this would be 0.2 recurring. So it's a lot easier for me to work in fractions. And it's a lot easier to add these fractions together if they have common denominators. So I haven't bothered to simplify any of these fractions for my working. I'll only simplify them at the end. And the probability that I have at least one yellow counter, I can add together all the possible combinations which include at least a yellow counter. Since they all have a common denominator of 90, that's relatively easy to do. That's 70 over 90, and now I can simplify that to 7 over 9. Or I could have worked it out by doing 1 minus the probability that there's no yellow counters. That's 1 minus 20 over 90, which is also 70 over 90 or 7 over 9. Now, how did you do with that? I hope you found that the probability trees are a nice way of visualizing all possible combinations of outcomes and helping you combine them in the right way. Please let me know down in the comment section if you found anything confusing or you think I've made any mistakes there. Otherwise, keep practicing and I'll see you soon.